Point north. Go ahead. Take out your phone. Open the compass app. It shows an arrow. The arrow points north. You trust it. Everyone trusts it. North is that way, except it's not. There is no north. Not really. Not in any permanent, reliable, absolute sense. What you call north is a temporary alignment with a wobbling magnetic field generated by churning liquid metal thousands of miles beneath your feet. That field is unstable, it drifts, it weakens, it flips, and the direction it points right now is not the direction it pointed 100 years ago. It's not the direction it will point 100 years from now. North doesn't exist, it's a convenient fiction we tell ourselves to navigate a planet that refuses to hold still. This should bother you more than it does. Let's start with what you think you know. The Earth has a North Pole. It's at the top. Santa lives there. Explorers plant flags. It's a fixed point, the northernmost point on the planet. True north. Except there are two norths. Actually, there are more than two, but let's start with the obvious ones. Geographic north and magnetic north. Geographic north is the point where Earth's axis of rotation intersects the surface. That's fixed. Sort of. It wobbles slightly over thousands of years due to precession, but for practical purposes it stays put. That's true north. The North Pole. 90 degrees latitude. Then there's magnetic north, that's where your compass points. And magnetic north is nowhere near geographic north. Right now, in 2026, magnetic north is somewhere in the Arctic Ocean, a few hundred miles away from the geographic pole. It's been drifting north-northwest at about 55 kilometers per year. Every year it moves. The compass that pointed accurately in 1900 is wrong now. Not slightly wrong, measurably significantly wrong. The magnetic North Pole has wandered over 1,000 kilometers in the past century. Why? Because Earth's magnetic field is generated by convection currents in the outer core. Liquid iron and nickel, heated by the inner core, rising and falling in complex patterns. These convection currents create electric currents. Moving electric charges generate magnetic fields. That's how Earth becomes a giant magnet. But the currents aren't stable. They churn, they shift, they change speed and direction. The magnetic field they produce is dynamic, not static. It's constantly evolving. And the place where the field lines converge, the magnetic pole moves around as the field changes. So when you point north with a compass, you're not pointing to a fixed location. You're pointing to wherever the magnetic field happens to be converging today. Tomorrow it'll be somewhere slightly different. 100 years from now it could be in a completely different part of the Arctic, or not in the Arctic at all. Here's where it gets disturbing. The magnetic poles don't just wander, they flip. North becomes south, south becomes north. This has happened hundreds of times in Earth's history. The last flip was about 780,000 years ago. Before that, magnetic north pointed to what we now call the South Pole. The field reversed completely, and it will reverse again. We don't know when. Could be 1,000 years, could be tomorrow. The field has been weakening recently, which some scientists think might indicate an upcoming reversal, or it might not, we don't know. The field is unpredictable. During a reversal, the field doesn't flip instantly. It takes thousands of years. During that transition, the field becomes chaotic. Multiple poles appear, the field weakens dramatically, compasses stop working reliably, navigation becomes difficult, and if you're asking what direction is north during a magnetic reversal, the answer is nobody knows. North ceases to have meaning. The field is too disorganized to define a pole. Now think about what this means. For most of human history, people navigated using the sun and stars. Those are reliable. The sun rises in the east, sets in the west. The North Star sits above the geographic pole. These are stable references tied to Earth's rotation, not its magnetic field. But when we invented the compass, we started relying on magnetic north. And we forgot that magnetic north is not a fundamental direction. It's a temporary artifact of fluid dynamics in the core. Stand at the equator, point north, now walk north, keep walking. Eventually you reach the geographic North Pole. You've arrived at the top of the world. Now which way is north? The question breaks. You're standing at the North Pole. Every direction is south. North doesn't exist here. It's not a direction you can point to, it's the point you're standing on. Direction requires context. At the pole, that context vanishes. But let's say you're navigating with a compass at the North Pole. The compass needle will point downward. It's trying to align with the magnetic field lines, which at the poles dive straight into the Earth. The compass becomes useless. It's not pointing north. It's pointing down. because magnetic north is not at the geographic pole. It's somewhere else, and the field lines curve into the earth. Your compass can't tell you which way to go because north in the magnetic sense is beneath your feet. Now let's talk about what north even means. It's a direction, but directions are relative. North of what? North is only meaningful if you define a reference frame. On Earth, we define north as toward the geographic pole. But why that pole? Why not the other one? The labels north and south are arbitrary. We could have called the South Pole north and nothing about the physics would change. The choice is cultural, not fundamental. And on other planets, the concept breaks down entirely. Mars has no global magnetic field. A compass on Mars doesn't point anywhere. There is no magnetic north on Mars. You could define geographic north as the rotational pole, but that's just a convention. It doesn't give you a magnetic direction to navigate by. Venus rotates so slowly that its day is longer than its year. Which pole is north? By convention, we pick one, but it's arbitrary. Even on Earth, magnetic north isn't where you think it is. Maps are drawn with north at the top. That's a convention. Cartographers had to choose an orientation. They chose to put the North Pole at the top, but there's no physical reason for that. South could be at the top. East could be at the top. The universe doesn't care. Up and down are local concepts tied to gravity. North and south are rotational concepts tied to Earth's spin. Neither is fundamental. Here's something nobody tells you. The magnetic field isn't even dipolar. We talk about a North Pole and a South Pole as if Earth's field is a simple bar magnet. It's not. The field is far more complex. It has quadrupole and octupole components. There are local anomalies. The South Atlantic anomaly is a region where the field is significantly weaker. Compasses behave strangely there. The field isn't symmetric. It isn't uniform. The simple picture of a bar magnet with two poles is a rough approximation. The real field is messy, and it's getting messier. The field has weakened by about 10% over the past 2 centuries. Some regions have weakened more than others. The overall dipole moment is decreasing. This could mean we're heading toward a reversal. Or it could just be normal variation. We don't have enough data to know. We've only been measuring the field accurately for a few hundred years. Geological records show reversals happen irregularly. Sometimes millions of years apart, sometimes tens of thousands. There's no pattern, no predictability. Now let's get philosophical. If north is just the direction toward a drifting magnetic pole generated by chaotic convection in molten metal, is it real, or is it a useful abstraction? You could argue that north is real in the sense that the magnetic field is real. The field exists, it has measurable properties, but the direction we call north is just one feature of that field, and that feature moves. So north is real, but it's not permanent. It's real right now, but it won't be real in the same place later. This is different from saying north is arbitrary. It's not arbitrary. The magnetic field determines where north is, but the magnetic field itself is dynamic and unpredictable. So north is determined but not fixed. It's real but not permanent. It exists but it migrates. This makes north a strange kind of reality. Contingent, temporary, evolving. Think about navigation. For centuries, sailors used compasses. They trusted them. Compasses pointed north. North was toward the top of the map. If you kept going north, you'd eventually reach the pole. Except you wouldn't. You'd reach magnetic north, which is not the pole. And magnetic north moves. So if a sailor in 1500 sailed toward magnetic north and a sailor in 2000 sailed toward magnetic north, they'd end up in different places. The destination changed. North shifted. Modern navigation doesn't rely on magnetic north. GPS uses satellites. The satellites know their positions relative to Earth's center of mass and rotational axis. GPS gives you coordinates, latitude and longitude. Those are tied to the geographic poles, not the magnetic poles. So GPS north is true north, not magnetic north. But most people still think of north as where the compass points. They conflate magnetic north with true north. They assume they're the same. They're not. Here's an experiment. Take a compass, note where it points. Now take a strong magnet, move it near the compass. The needle swings toward the magnet. You've created a local magnetic field stronger than Earth's field. The compass now points toward your magnet. Is that north? According to the compass, yes. The compass doesn't know the difference. It just aligns with the strongest magnetic field, Earth's field. Your magnet's field doesn't matter. The compass follows the field. So what is the compass measuring? Not a direction in any absolute sense. Just the local orientation of the magnetic field. If you're in a building with steel beams, the compass might point toward the beams. If you're near power lines, the compass might deflect. The compass isn't finding true north. It's finding the direction of the local magnetic field, which is influenced by everything magnetic nearby. North is just whatever direction the local field happens to point, and that direction is contingent on your surroundings. Now think about ancient humans. They didn't have compasses. They navigated by the sun and stars, the sun's path across the sky, the position of constellations, the North Star. These are tied to Earth's rotation. They're stable over human timescales. If you can see the North Star, you know which way is geographic north. That's reliable. That doesn't drift, but it requires a clear sky. And it only works at night. During the day, in clouds and storms, you're lost. The compass changed that. Suddenly you could navigate in any weather, day or night, cloudy or clear. The compass always pointed north, except it pointed to magnetic north, not true north. And sailors had to learn the difference. They had to account for magnetic declination, the angle between true north and magnetic north. That angle varies by location. In some places, magnetic north is east of true north. In other places, it's west. And the angle changes over time as the magnetic pole drifts. Maps started including declination diagrams, little arrows showing the difference between true north and magnetic north for that location at that time. But those diagrams go out of date. The pole drifts. The declination changes. A map from 1950 has a different declination than a map from 2020. If you navigate using an old map and a compass, you'll be off. Not by much, but enough to matter over long distances. Here's the truly strange part. The magnetic field isn't just drifting, it's weakening. If it keeps weakening, it could collapse temporarily during a reversal. When that happens, Earth loses much of its magnetic shielding. The field deflects solar wind and cosmic rays. Without it, more radiation reaches the surface. This could affect satellites, power grids, communications. It could increase radiation exposure for astronauts and airline passengers. It might even affect life on the surface, though the atmosphere provides some shielding. But we don't know how bad it would be because we've never experienced a reversal. The last one happened hundreds of thousands of years before humans developed technology. We have no records. We can look at geological evidence, magnetic minerals in rocks that recorded the field direction when they formed. Those records show reversals happened. They show the field weakened during transitions, but they don't tell us what it was like to live through one. We're extrapolating, guessing, hoping it's not catastrophic. And while the field is weakening, magnetic north keeps drifting. It's been accelerating. It used to drift about 15 kilometers per year. Now it's moving 55 kilometers per year. Why the acceleration? We don't know. The core dynamics are too complex to model precisely. We can measure the field, we can observe the drift, but predicting the future is difficult. The system is chaotic. Small changes in core convection can have large effects on the field. So when you point north, you're pointing toward a moving target, a target that's accelerating, a target that might flip to the opposite direction someday, a target that only exists because of turbulent convection in liquid metal you'll never see. That's not a direction, that's a guess. Now let's talk about what happens at the magnetic poles themselves. If you stand at magnetic north, the field lines are vertical. They go straight down into the earth. A compass needle wants to align with a field. At the equator, the field is horizontal, so the needle stays level. But as you move toward the poles, the field tilts. The needle tilts. At the magnetic pole, the needle points straight down. It's trying to align with the vertical field. This is called magnetic dip or inclination. Compasses are designed for use at mid-latitudes where the field is mostly horizontal. Near the poles, they don't work well. The needle drags on the compass housing. It doesn't spin freely. You can't navigate by compass at high latitudes. You need other tools. GPS, stars, dead reckoning. The very concept of using a magnetic compass to find north breaks down where north is supposed to be. And here's the final twist. There are multiple definitions of north. True north, geographic north, the rotational pole, magnetic north, where the compass points. Grid north, the direction of north on a map grid, which is slightly different from true north because maps are flat and Earth is round. Projections distort directions. Then there's celestial north, the direction toward the north celestial pole, which is almost but not exactly aligned with the rotational pole because of axial precession. So when someone says north, which north do they mean? The answer depends on context. For navigation, probably magnetic north. For cartography, probably grid north. For astronomy, celestial north. For GPS, true north. They're all slightly different. They all shift over time at different rates. None of them is the one true north. They're all approximations, useful fictions, tools for orientation in a world that refuses to provide absolute reference frames. You think north is a direction, but direction requires a reference. On Earth, we use the magnetic field, but the field changes. On a cosmic scale, there is no up or down, no north or south. Those are local conventions tied to Earth's rotation and magnetic field. Change planets and the conventions change. Leave the planet entirely and they vanish. In interstellar space, which way is north? The question is meaningless. There's no magnetic field, no rotation to define poles, just arbitrary choices. So when you point north, understand what you're doing. You're pointing toward a temporary feature of a dynamic magnetic field generated by processes you can't observe in materials you'll never touch. That feature is moving. It might flip, it might disappear. It's not a fundamental direction. It's a local, temporary, contingent orientation that exists right now because of the specific state of Earth's core today. North is real, but it's not permanent. It's not absolute. It's not even in one place. It's a moving target in a chaotic system, a useful abstraction that helps you navigate, but an abstraction nonetheless. The universe doesn't have a north. Earth barely has one, and the one we have won't stay put. Maybe that's the deeper truth. Directions don't exist in any absolute sense. They're relationships. North is just the direction toward a magnetic pole, but the pole moves, so north moves. The relationship changes. What you call north today is not what people called north 1,000 years ago. It's not what people will call north 1,000 years from now. You're navigating by a shifting reference in a turbulent system on a spinning rock hurtling through space. And you trust your compass. You trust that little needle. You believe it points north. And it does. For now. Until the field drifts a little more. Until the pole wanders a little farther. Until the whole thing flips and north becomes south. There is no north. Just a temporary alignment you mistake for permanence. A wobbling field you mistake for stability. A moving target you mistake for a fixed point. You've been pointing the wrong way your entire life. And tomorrow you'll be pointing a different wrong way. Because north doesn't exist, it's always somewhere else.